So let's talk a little bit about the Coulomb's law and specifically how is it that magnesium and barium have different solubilities. So magnesium hydroxide is not soluble in water and barium hydroxide is. And so the general conclusion here is that since they're technically both ionic, they should be soluble, but there's something strange happening here regarding Coulomb's law and its charges. And the reason why is because magnesium is attraction to the hydroxide is a lot stronger than barium's, that when you put it in water, they're not going to be able to separate as much. And so let's talk a little bit about why that's the case. So in this specific case, if you take a look at the ion dipole forces between magnesium and barium, we can see that the attraction is much larger, even though they both have 2+ charges. So let's assume everything in terms of the charges are the same, but we're taking a look at the size of it. Because magnesium is a smaller ion, it's going to have a shorter distance between the negative and dipole and protons, while barium has a longer distance between those negative and dipole protons. So the charge here is going to be a little bit different. So when you're talking about this attraction, if the attraction, the distance is farther apart, they're not going to be able to have that interaction as readily as something else. And so when we're talking about iron dipole and intermolecular forces, what we're really talking about is two forces work against one another. One of the forces is going to be stronger than the other. One of them is because of the fact that there's an attraction between the ionic bonds, and there's also an attraction between the water molecules through this dipole moment. And so if you think about it for a second, it kind of makes a lot more sense, right? We always assume, like, for example, something like NaCl is going to dissolve in water, but because Na is actually a pretty small molecule relative at ion relative to some of the other ones in its same group, that attraction is going to be a little bit easier for sodium to kind of break apart. But if you compare it to something else like, for example, magnesium and barium, something a little larger would become even harder. It would be easier. So if we're taking a look at these examples, the larger the ion is, the more likely it's going to be more soluble. Second thing also has a lot to do with the attraction with the water. So it's kind of like not a hard and fast rule, but generally speaking, you're talking about charges attracting each other within the ionic bond and also an intermolecular force with the water. Alright, now chromatography is another way of separating out specific chains. So we've kind of learned a little bit about solubility, but if you take a look at chromatography paper has nonpolar and carbon chains in it. It's got OH groups that can readily form hydrogen bonds. So if you take a look at this paper as an example, the maximum height traveled by a nonpolar solvent would be up here. The distance traveled by the solute by A and B would be indicated by this red and this green line. And the solution, which is a nonpolar solvent, usually is going to have solute A and solute B are going to be at the bottom. So again, when we're talking about chromatography paper, we're talking about these OH groups that can form those. So the more polar something is, the more likely it's going to run up. Now the stationary phase in chromatography and the mobile phase. So what happens here is in chromatography paper, you're going to get areas where the solution can actually run or areas where the solution kind of gets stuck. So as the solvent moves up the paper, it carries some of those particles with it. And that distance that we're getting really depends on the attraction of that paper. So obviously, the further up it goes, the more attraction it gets with the paper and also with the solvent itself. So we've got a couple of forces that we have to discuss. So the solid particles that can form the hydrogen bonds at several locations along the structures will not travel very far up the paper. So most of the molecules in the paper contain many hydroxide groups. So generally speaking, these solid particles will form H bonds with the paper relatively close to the solution surface. So they're going to get stuck pretty easily. Solid particles that are mostly nonpolar will have weak attractions for the paper and relatively strong attractions for the nonpolar solute. So what you're talking about there is these particles will be deposited further up the paper. So if we're talking about things that are going to stick or going to travel, you're talking about really nonpolar versus polar areas. So I want you guys to really think about this idea of hydrogen bonds as they're traveling up the paper. So the ones that actually have more attraction are most likely going to get stuck, where the ones that don't have attraction are probably going to move up a little further up. So here's an example of solid solubility and temperature. So if I increase solid solubility, you're going to get more solubility for it. So a classic example here is something like NaCl. Let's bring it up to a boil at about 100 degrees Celsius. But potassium nitrate really starts dissolving at a much higher temperature, much more solubility than something like NaCl or KSO4. So generally speaking, the more temperature, the higher temperature you have, the more solubility you're going to get. All right, so here's another example called fractional distillation. So fractional distillation is a separation of volatile liquids in a liquid-to-liquid solution on the basis of boiling points. So if I give you, for example, a mixture and it has other sort of liquids in there, if I boil them at a specific temperature, the one that's being condensed that has a higher concentration is the one with the higher vapor pressure. So if I'm trying to separate out the vapor in this area, what I can do is boil it at different temperatures. And the one I'm actually collecting is going to have the one that's going to have higher vapor pressure. By definition, is the stuff that actually kind of boils out. So the cycle of boiling, condensing is repeated enough times, you can actually purify enough of the volatile substances in there. Now, in terms of gases tend to increase, the solubility of gases tends to decrease as temperature increases. So if you think about it for a second, if I heat something up, I'm most likely going to get the gases coming out of the liquid. And generally speaking, it's because gases have weak intermolecular force. So an N2 versus an O2, they form pretty weak dipole movements and with water. But as I increase the kinetic energy, the particles are going to break free and then they're going to enter in the gas phase, especially if they're inside that liquid. Now, here's a classic example of fishing and somebody who studies chemistry versus somebody who doesn't. So if you go fishing and you wanted to go fish on a really, really hot day, generally speaking, you're going to find that if you want to get optimal fishing and you want to get the most fish, you want to find out where the fish are, right? And the way the fish have to do is that they actually love to be near oxygen, because fish are like us. They need oxygen, they need water, they need all that stuff. And so when it gets really, really hot, what ends up happening is that you're going to get, in the hot water that's closest to the sun, you're going to get less O2. However, if you have cold water, you're going to get more O2. So during very hot days, the fish are not going to hang around on the surface. In fact, they're going to be hanging around at the bottom where all the oxygen is. And so a person on the left, which is a very smart person, decides to put the rod a little further down to catch fish, while the other person is not. Another example is going to be beverages. For example, warm carbonated drinks go flat faster than cold ones. So if you think about it, if you put a can of Coke in the refrigerator, it's going to have more gas inside than something where you're going to leave it out. And the classic example of this is that solubility. As the gases begin to pick up kinetic energy, they're going to get out of that gas phase and acquire more vapor pressure. Another example is called thermal pollution. So usually when you have industrial processes where water's pumped out of lakes or rivers and they use it to cool things, what happens is that you end up getting a lot of that, again, solubility. Those gases kind of come out and the heat flows into this water. And once it does that, if you dump it right back into the lake, wherever you're pulling it out from, then at that point, a lot of the fish are going to die. And the reason why is because you're going to increase that temperature. And because you increase that temperature, the O2 levels drop and then you have issues. So thermal pollution is a very interesting thing, because many people say, well, I'm not really polluting the environment. All I'm doing is I'm pumping water out and pumping right back in. But by doing that, you're changing that temperature, and then you get all these other issues that come with it. So gas solubility and pressure really comes down to this idea called Henry's law. And Henry's law is indicating that pressure only affects the solubility of gases, and it's directly proportional to the partial pressure of the gas above the solution. So we're not really talking about pressure in terms of solids or liquids. We're really talking about the proportionality of these partial pressures. And so here's an example of that. So if we take a look at gas P1 versus P2, in this case, we're trying to push as much gas inside this aqueous solution. So when PA is very small, what's the pressure for PA is small, A in the solution is low. However, if I increase the pressure, now you're beginning to put that gas and force it inside that liquid. And so at that case, we're going to get a high pressure because the gas is inside now in the liquid. Now, the best example of this is carbonated drinks, going along with Henry's law, right? So if you take a look at Coke here, or Pepsi or whatever soft drink, and I get 4 atm, what I'm actually doing here is I'm actually calculating the concentration of CO2, which is about 0.1 mole. Now, if I reduce the pressure down to 3 times 10 to the negative 4, the CO2 begins to leave the solution as PCO2 on the surface of the liquid has decreased. So normally when you open up that bottle cap, you are actually releasing some of that pressure out, and now the soda comes up. At 3 times 10 to the negative 4, at some point your concentration of carbon dioxide eventually goes flat. So now you have 9.9 times 10 to the negative 6 moles. So bottom line is that if you increase the pressure, you're going to push that gas into the liquid. Now here's a classic example of graphs and pressure. So different gases have different solubilities. So if I take a look at H2O2 and NO, the slope of these lines indicate the intermolecular forces. So the steeper the slope is, the more attractive these forces are together in the gas phase, and the more likely you're going to have to really increase that pressure to get more solubility in. Okay, so NO is going to be higher. You get higher solubility as you get that pressure in. Same thing with O2 and N2. So here's a classic example of called the bends. The bends is an example where anybody who scuba dives underwater, you're going to get a solubility of N2 in the blood. So at sea level, you don't really get a lot of the N2 inside your blood, thankfully. However, once you get to high pressure, you increase that pressure, the N2 gets more soluble, and now we're having issues. So if you ascend too quickly, what's going to happen is that the reduction in the pressure causes the N2 aqueous solution to form in your blood. So what ends up happening is that gas starts to go backward the other way, and once it turns into a gas, it will actually go into your bloodstream. And deep sea divers usually prevent this by using helium. Okay. All right. Well, thank you very much for listening.